Okay, I think everybody should be here now. I welcome everybody to this webinar about mastering graph analysis and layout. My name is Benjamin Niedermann. I'm a software developer at Yworks, and I'm happy to welcome you to this episode of the series, The Art of Graph Visualization. In this series, I show you how to create graph visualizations for your connected data that are not only beautiful, but also meaningful and useful. And with meaningful and useful, I mean that you can actually get new insights from these graph visualizations for your connected data. In the very first episode of this series, I gave a broad overview of the most important aspects about creating graph visualizations, including the problem setting, the analysis, the layout, styling, and interaction. And then in the second episode, so the last episode, I also argued that it's really important to separate or to also have a preparation phase where you first consider the problem setting and think about what you would like to answer on your data before you start creating the graph visualization. And today, I would like to focus on analysis and layouts and discuss how to use this information that we gained from the last episode in order to now decide which kind of layout we would like to use for our graph visualizations. So to that end, we also will consider graph analysis, and we use this graph analysis to gain new information, but also to annotate the data, so to pre-process the data so that we can easily create graph layouts or graph visualizations with our data. And then in the second part of this webinar, I will also talk about layouting graphs, so about how to place the nodes and route the edges. And in particular, I will also talk about how to route or how to find a suitable layout style that is suitable for your data. So the webinar will be structured as follows. At the very beginning, I will introduce an example that I will use as a running example throughout this episode, but also throughout the next episodes of this series. The idea is that I not only give the theory behind, for example, the layouts, but that I more focus on examples showing you how to do this, also giving you ideas how you can transfer this to your own problem. So after introducing this example, I then will also talk about analysis techniques. There are many out there that you could use to analyze your data, especially if you already have translated this to a graph structure. And then in the second part, as I already said, I will talk about different layout styles that you can use to visualize your connected data. Here, it's important to say that I don't consider the graph analysis by itself, but always in the context of graph visualizations. So the idea is that we actually gain information from this graph analysis that we can then use in our layouts, for example, to decide which kind of layouts we would like to use, but also as an information for configuring these kind of layouts. And then after this part, I will also go more in detail of this example that I've introduced at the beginning and will show how to create a layout. This will be a bit more practical. So there I will sketch also how to proceed or how to do this in general. And then finally, at the end, in the conclusion, there will be also a question session where you can ask all your questions. So if you have some, then please feel free to just write them down into the chat. And then at the end of this webinar, I will try to answer them. In case that you watch this video, because this will be also uploaded to YouTube, then please feel free to use the comment section below the YouTube video, and we will try to answer your questions as soon as possible. Or otherwise, just send us an email and we will also reply as soon as possible. So let's start with the main part of the webinar, and I would like to start with the example that I would like to use as a running example. And as I already introduced in the very first episode, this is an example that is based on a music database, which is called Discogs. This is a really large database on audio recording and artists, which is basically a Wikipedia-like database, which means that the users can actually insert and edit entries. So it became a really large database over the years. So for example, there are more than 16 million entries for releases and more than 80 million entries for artists. And the idea is that we would like to create graph visualizations that help us to answer some questions on these databases. In the last episode, I showed different questions that you could try to answer on this database using graph visualizations. And today I would like to pick one of these questions. And for this question, I would like to create this graph visualization. And the idea is that we would like to learn something about the history of artists. So here the idea is that yeah, we would like to learn, for example, for one artist, how his music life was. So in which bands was the artist, and which band did he or she join first and then second, and so on. One moment. So in this example here, you can see, for example, the path of Paul McCartney. One moment, I just want to annotate this. Yeah. And we would like to see the life of Paul McCartney regarding his life in music. And what we can see is he has first joined the Beatles, and then the band Linda Paul McCartney, and then he also joined the band Wings. And we can see this following this blue path here. And the same we can also do for other artists. And sometimes these paths joined together, and then we know they are in the same band. And this is a visualization that we would like to create. And of course, we would like also to integrate maybe further information, not only this, maybe genres that we would like to introduce, but also, of course, the timeline. So it would be nice if we could have some kind of flow showing the time, how it proceeded. So in this case, we have a top to bottom flow. And this is the basic idea of this visualization, and I will explain in today's webinar how we can get the graph structure from the data, and also how to get the first layout of this data. So let's go to the data. I just want to show you very shortly how the data looks like. So I've extracted this basically from Discogs. So I just extracted this from a subset of artists. It's basically a JSON file that consists where each entry is basically one artist. And then we also have some information about the groups in which the artist was. And of course, we have the name. And if you scroll down a little bit, for example, yeah, to this point here, then you see that there are also entries about the groups, so the music groups. So for example, here's the music group California, and we also have the an information about the first release and the last release, but also about the genres and how many releases we have in these genres. And this information is basically what we are given to visualize our graph. So this information I've extracted before this webinar. This database, of course, contains much more information, but for the purpose of this presentation, I reduced the amount of data. So the first thing that we need to do is to think about how we could analyze this data. And one way to analyze this data, so with analyzing, I mean to get some information about the structure of the data and what kind of data there is actually in this JSON file. And in order to do this, what we can do is we can just create a basic graph structure based on this data and then analyze this graph structure. And of course, what we can do at the very beginning is we can just consider the basics of this graph structure. which basically means that we consider the number of nodes, the number of edges, so very fundamental properties, but also the in-degree or out-degree. So the in-degree is the number of edges that go into the node. Here in this case, we have an in-degree of 2. And the out-degree is here the number of 3. We have 3 outgoing edges. And of course, we can also consider other things like number of leaves or the density. There are many basic properties. And I also would like to do this for this data set. So I now go to the playground, and in the chat you also should get some link for this playground, and you can play around with this using Y-files for HTML. So basically it's a very simple possibility to create graph visualizations just in a kind of sandbox where you can play around with this. And if you don't have the link, you can also go to our website and go to the playground there. And then here in the examples menu, you will find this example here, discogs.com data analysis in the examples. And what you can see is that I don't want to give too much details for the code in this webinar today. So if you are not too much into coding, I will try to be very on a high level. There will be an extra webinar where I really will discuss the coding details about this. So about this follow-up webinar, I will also give more information at the end of this webinar. But just to give you an idea, what I do here is I load the graph, and then I also do some kind of layout just for presentation reasons, and then I analyze these properties. And I just click play here, and now it's just computed this on my computer. This layout, I used an organic layout. And we have here these red nodes and the yellow nodes. And the red nodes, that should be the groups, the music groups, and the yellow nodes are the artists that I've collected and for which I have extracted the data. So typically, your data is too large probably at the beginning to just visualize it, or maybe you can do this, but it won't help you. Typically, you really want to get some numbers. I just did this in order to show you how the graph looks like. And now I should also explain at this point how I connect these nodes. So what I do is, for example, if we look at this, this is an as I said, this is a music group and this is an artist. So this is a music group and this is an artist. And I've connected them if the artist was member of this music group. So it's a really simple relation. And of course, what can happen is that multiple artists, for example, these 3 here, have been in the same music group. And then we have here this music group, and these 2 artists were in this music group as well. So we get some kind of information about how our data looks like. And if we just clear this, and if we have a look at this very simple layout, we already get some kind of information like, okay, there are some disconnected components, so they are not all connected in this network. And then we also have these artists with these many single music groups. But of course, sometimes you don't want to visualize your data first, but you first want to analyze this, getting some numbers. And for this, you can basically just do some basic analysis, like I've done here in this analysis basic properties, where I basically just output the number of edges, the number of nodes, and the maximum in degree and the maximum out degree, and so on. And I just output this here in this terminal, getting some basic information. And what I get is, for example, that this graph consists of 211 nodes and also of 263 edges, so it's basically in balance. And we have a maximum out degree of 14, which is for us an important information actually. So if you recall how we would like to create the visualization, so what we would like to do is that the artist is at the top of the visualization, and then we would like to add the groups he was member or she was member of as a path of this artist. And maybe we have another artist, artist 2, and they join at some point and then they leave again. But this path here, the length of this path corresponds to the out degree of to the maximum out degree. So the maximum length of this path. So the artist with the longest path has a length of 14, because in this data here, what we get is an artist that is just connected to 11 not to 11 but to 14 other music groups. So this already gives us some information about how our visualization will look like. So what we need to consider is that in our target visualization, we get very long paths. So paths with 14 nodes could be already very long in this kind of visualization. So going back, the next thing that you could analyze is not only the basic properties, but maybe also more interesting properties like the connectivity. And connectivity means that we just count the number of components that the graph consists of. And as you already have seen in this picture that I've showed you before with these red and orange nodes, we have several components, so it's not a connected graph. So in the undirected case, these two are connected components, but the entire graph here is unconnected. So basically there are two nodes where we can't find any path between these nodes. And this is also an important information for our graph visualization, because then we need also to think about how to arrange these components. Do we want them to just place them besides each other, or do we want to nest them each other somehow, or how do we want to tackle this problem that we have multiple components? For the directed case, there are further informations that you can also take from this. So for example, there are strongly connected components and weakly connected components. Strongly connected means that every node is can be reached by a directed path from another node. So here it's very obvious. We have multiple cycles here inside. So this node can be reached from any of the other nodes using these directed edges. Weakly connected components are components where when you replace these directed edges by undirected edges, then the graph is a connected, the component is connected. So basically it's just mapping it to an undirected case. And this is of course also what you can analyze this in our example. So let's have a look at this again in the playground. So going back to the playground, and what we can do is we can analyze the components. And for this purpose, for example, Y-Files, one of the main products of Y-Works, offers simple algorithms or algorithms that you can simply use with 2 or 3 lines of code. Here, for example, we just use the graph and run the connected components algorithms, and then we get some results on how many components we have. And if we run this, we again get the visualization. We find out that we have a number of components of 4. If we look at the visualization, we have here these 4 components. And what we also can do, and this is also very important, is not only to look at the number of components, but also at the sizes of the components. So what we can see is that we have one large component with 189 nodes, and then we have 3 very small components. And this is also also an important information for our graph visualization. So maybe one decision could be that we just skip these three components and say, okay, we are only interested in the largest component. Or another thing, it could be that we say, okay, we reserve a lot of space for the large component, but only small spaces besides this for the small components, arranging them, for example, in a column. And so we can basically decide on how to create or which kind of layout we would like to have in a broad way. So the next property that I would like to consider, so I won't consider all of these graph analysis properties because this would be too much for this webinar, but I just want to show you some of them. I will later on point you also to literature that you can have a look at to learn more about this. So let's have a look at trees and cycles. And this is also an important information that you can acquire before layouting your graph, and which helps you to decide on the layout. And what do I mean with trees? Trees are a very special type of graphs. They are connected and have no cycles so if we consider them undirected, so this, for example, would be a tree, and these red nodes are the leaf nodes, and the blue nodes are the internal nodes. And what we also see here is an case where we don't have a tree. Here we have a cycle. So if you walk along this path here, then the cycle closes with this blue edge, and this is then obviously not a tree. And a set of trees is, of course, called forest. And the question is, do we have a tree as data structure or not, or as graph structure? And this is already an important information, because for trees, there are very specialized algorithms that can use this information to optimize the layouts. The next question that we can also answer in the same way is whether the graph is acyclic, directed, acyclic. This will be also important. For us, so acyclic or directed acyclic means that all edges are directed and there are no cycles. Here, for example, we have an directed acyclic graph, which basically represents a topological order. And here we have a non-acyclic graph, so we have here some cycle that is directed, and we can walk along the cycle. So we have some information. If you assume that this graph represents some information, then we also get this information that something goes around in the cycle. Why is this information so important for us when thinking about layouts? Again, similar to tree layouts, knowing this information, we then can apply certain algorithms that can help us, or we can apply certain layouts that can help us to express certain informations. As you can see here already, and this is not done by accident, but by purpose, is that basically all edges, apart from this one, points upwards. So what we can basically get is an upward directed drawing where all edges point upward, or we also have here these same layer edges. And of course, we can use this to express information. So for example, to express some kind of temporal information. So we could say, okay, assuming that these nodes represent events, we could say, okay, this event occurred before this event, and this event occurred before this event, and so on. So basically, this gives us some kind of possibility to express or to encode information in our layout. And of course, you can, again, analyze graphs automatically to gain this information. So let's go to the playground again. And And here I have this function analyze cycles, and this basically does this. So what it does is very simple. It uses the algorithm which just called cycle, and this algorithm computes a cycle in the graph if there is some cycle. And what I do is I say, okay, consider the edges as undirected edges, which basically means if I don't find any cycle inside of this graph, then the cycle must consist of trees. So it's basically, we know that we already have several components. So then we know that each component must be a tree. So I run this. I can run this shortly. And we see here is a tree, and the answer is false. No, it's not a tree. And of course, by just looking at the image, we can also decide on this very easily. We can find cycles, but recall typically in the very first phase when thinking about the data, you probably don't have a visualization, and then it's helpful to do this programmatically without visualizing it. The next test is whether the graph is acyclic, and here the trick is that I just say, okay, I'm only interested in directed cycles. I already know that it's not a tree, so it has some cycles, and now I ask whether there are directed cycles. And when I run this cycle test, I get the information. No, it's not a cycle. It's not, it has no directed cycle, so it must be acyclic. And actually, this is not very surprising if you think about how we have constructed the data. So the idea was, we call this is that we have an artist, and we said, okay, we connect the artist to his or her groups by just introducing directed edges that point to these groups. And of course, another artist, we have also these directed edges, but what we never will have is an edge that goes back to an artist, because we don't do this by definition. And this basically says, okay, it must be an acyclic graph. But sometimes you have data where you can't be sure about this, or you don't know how many cycles you have, or you would like to get some guess of how many arcs or edges you need to remove to get an acyclic graph, and there you can use such techniques. So this gives also some information and will help us later on to decide on the layout we would like to use. So the next part is clustering. So clustering is a really, really large topic. And there are many different things or algorithms that you can use to find clusters in your graph. So basically groups of nodes that somehow relate to each other. So here we have some kind of clusters. And for our use case, or for this example, I decided to consider bi-connected components. But you could also use different clusters having different meanings. And a bi-connected component means just that removing one of the nodes, then the component remains connected. So for example, this component here is connected, but when I remove this node, it will split into two components, so it's not bi-connected. If I look at this structure here, this is bi-connected. So if I remove any of these nodes, the component still remains connected. Of course, if I remove a further node, then it could be that it's split, but removing only one node, the component remains connected. And here these colors, for example, indicate the components, and the blue nodes here, for example, indicate tree components. And here we also have cycles. And this also gives you some kind of information on your graph. And what we can do is we can analyze or find all bi-connected components. What I will do here is I just use this biconnected component clustering algorithm, I run it, and then I create a histogram that tells me how many biconnected components I have. So for example, in this case, I have one very large biconnected component. Oh, no, I'm sorry. I have one biconnected component with 61 nodes, but I have many components that only consist of one node. So basically, for example, if I remove this node here, all these will be separated, all these will be components. So what this basically means, or what this statistic here tells me, is that this graph consists basically of one core component, basically. This is this one, but there are many leaf nodes basically attached to this component. And this is also maybe important to know for each other, for us. So in this case, we can say, okay, there are many music groups that are only attached to one artist. Maybe we need to think about how to reduce the amount of information. So maybe by just excluding them so that we don't show them. And this actually I will also do later on. So, and this again gives you some kind of information. And as I said, I can't do all of these analysis techniques in this webinar. This would be too much. But if you are interested in finding out more about this, then please feel free to just have a look at our demos where we also just visualize the ideas of these analysis techniques. I just have a short look at this demo. You can also find this on our homepage, and we will also add some link to this demo below the YouTube video. And what you can do is here you can go through all these samples, and then you can also decide on which kind of algorithms you would like to run. So we could use centrality is a nice one. One moment. Yeah, closeness centrality is a very typical analysis property that you could consider. And then the algorithm is run, and then the centrality basically says which of the nodes are most central in your graph. So here we have a centrality of 1. So this is a really central node. And then we have nodes that are not that central. And then what you could also do is count how many central nodes you have and how many nodes are not that central. And this also gives you an idea on how your data looks like in this graph structure, and you can interpret this. And what you can do is you can just go through these algorithms and then play around a little bit with this. So here I just apply the cycles algorithm, finding cycles in this graph. If you want to know more or read more about this, there's of course a really, really large set of research papers that you could consider and start with. I also could, oh, no, I've closed my presentation accidentally. One moment. That sometimes happens if I press the wrong button. One moment, I just restart it to the right point. Okay, I think we need to just go through these examples here again. By the way, this entire presentation is also a graph visualization, as you maybe already have noticed, and this graph visualization is also done in Wi-Fi's HTML, which basically supports things like these animations and popping up new nodes, and allows you to style the nodes using images so that you can actually do this like here with this presentation. And I think we were here, and what you also can do is that you can have a look at our documentation. So we have an D guide where we explain in our documentation not only the API, but also the ideas behind these algorithms. So for example, if you go to the closeness centrality, you will find further information on the ideas of this, but also coding examples. And this maybe is also a good starting point for you to just see what kind of analysis techniques are there out there, and then you can just see how to apply them. No, I just went to the API. I just wanted to show you, this was the one example, centrality measure here. It's basically an article about how the centrality measure is used and how you can use it for your graph data. And it gives you already some ideas how to do this. So I now would like to use this information to decide on the layout. So which layout should we use for our graph visualization? And to that end, we should have in our mind these numbers that we just have gained from the analysis. But of course, we also should think about the idea of the visualization, what we would like to visualize. And here I would like to recall that that we would like to have these artists and visualize their paths in their music lives, going from one music group to another. So what I would like to do now is to go through of these layouts, or at least some of these layouts, and discuss shortly when to use them and what kind of properties they have. And then I will also tell or explain why I have chosen a certain layout for our example. So I start with the organic layout because this is a very typical layout that often is used if you don't know too much about your data. People often use organic layout. It's a force-directed layout, which basically gives you already some kind of layout. So in this playground that I've showed you before, I also applied an organic layout because I didn't know how the structure of the data is. So in that case, you can just use the organic layout to get some natural distribution. Typically, symmetric properties are represented very well in these kind of layouts, and nodes are placed very closely to their neighbors. So for example, here, these neighbors are very nicely placed to each other. And so you basically get some ideas of how the neighborhoods are. So typical use cases are, for example, social networks, where you would like to visualize connections between participants of the social network. In our case, I would say this is not very suitable. So you can apply organic layouts on really large graphs. And so this is no problem, the basic properties, but the problem is that we cannot basically express the structure that we would like to show. So we would like to show this temporal structure, so this top to bottom flow. And with the organic, this is a bit difficult. You can introduce constraints. So for example, the organic layout offered by Y-Files also allows you to give constraints, but for our purpose, I think this is not suitable at this point because we have too many constraints. So let's have a look at another layout. So let's have a look at the circular layout, which is very nice for bi-connected components. So what it does is basically it visualizes a tree structure, and some of these nodes are not nodes, but they are components of the graph. So if you look at this, we have here this kind of tree structure. And this is a single node, basically, and this also, and this also. And then we have here this kind of tree structure and so on. And what it does, it shows you how these bi-connected components are connected with each other. And then for each component of each of these nodes, you also get this information how these intranodes of these components are connected with each other. this is also a very nice layout to show. To show such, to emphasize groups and the tree structures connecting these groups. In our use case, again, I would say, okay, maybe if we would like to visualize other information in this graph, especially in the base graph that we are given, then we could use it as our graph is not too large. But especially if you have a lot of edges within the groups, then you also need to think about how to handle these edges. So for example, using edge bundling in order to get rid of this clutter here. But for our use case, I would use another layout. The radial layout is a very systematic layout. It's basically a kind of tree layout with the support of also, of course, non-tree edges. But basically, it's really useful for tree layouts where you have one node in the center where you say, okay, this is the most important nodes. It should be in the focus of the view of the visualization. And then you may have some other nodes that are level-based around this center node. So they are on concentric circles. So what you could say is here that it's basically a kind of visualization for reachability. You could say, okay, maybe this is a city and these are cities that are reachable with a certain time from this node and then the next ring of cities and so on. So this would be a very typical example. So one node that is in the focus of the graph, and then there are many other nodes that somehow relate to this node with their distances. And this is a thing that you can easily visualize with this. In our case, you could think about this visualization if you only have one artist and you could in the middle, and then you have other relations, maybe to music groups or releases or something to use this. But as we have a lot of artists and each of these artists has the same importance, basically, I would not use here the radial layout where I would need to decide on one artist to place. Or you just have a very different idea how to use this visualization. Mhm. So the next layout that I would like to consider is tree layouts. Here we already have this top to bottom structure, which you can, of course, use to somehow visualize temporal information, but typically tree layouts are used for hierarchical structures, so parent-child relationships are emphasized, and it's typically assumes, or the basic assumption is that the graph is a tree. So we found out for our graph that it's not a tree, but acyclic. Actually, our tree layouts of Y files typically also allow you to have non-tree edges. So for example, it could be that you have some edges here or here. This would be also okay. What the algorithm basically does, it first ignores these non-tree edges, then it creates the layout of this tree. So it places the nodes at edges and routes the edges, and then it introduces these non-tree edges routes between the nodes. So you could actually use this already for layouting our data because we basically have this kind of structure with the difference that we don't have, for example, one root node, but we have a lot of artists that all of them are basically roots. This, as I said, is maybe more suitable for structural diagrams like, let's say, organization charts where you would like to show the hierarchical structure of a company, something like that, or a family tree. Here you can typically use tree layouts. And now I come to the layout that actually suits our use case very well. It's the hierarchical layout. And this is a layout that is really made for acyclic graphs. And again, as you may already have noticed here, not all edges need to be acyclic. Here you have a cycle. So you could go here along this. Maybe I should redraw this. So here you have a cycle. So this graph is actually not acyclic, but basically, if you assume that you have not too many cycles in the graph, the hierarchical layout really is a good choice for showing such diagrams. Because it has this idea that you have some top to bottom flow, for example. So you have some main flow. So most of the edges go downwards, only few go up. And you still can allow these non-directed cycles. So for example, here you have a non-directed cycle. If you make all edges undirected, you get this cycle. So it's not a tree. And for these purposes, you can use the hierarchical layout. The next nice feature of this layout is that it also allows to introduce constraints and in a different way. So for example, what you could say is, and actually can do this with our algorithms, you can configure them like this, that you, for example, can say, okay, I would like to have all these nodes here on a common line. I really want to enforce them to lie on this common line. Or I could say, okay, I would like to have this node lying below this node here. So that I also introduce constraints expressing this relative information where some node lies, whether it lies to the below or up another node. What you can also do is you can introduce sequence constraints or so-called sequence constraints, saying, for example, that I use a different color here, that, for example, this node should lie to the left of this node. And again, you can introduce really strong constraints between nodes of the same layer, basically. And actually, I will use this for our example to create the layout. You will use the hierarchical layout because it suits our parameters and the idea of our visualization best. Finally, I would like to mention another very small kind of layout, namely the compact disk layout. This is one of our smaller algorithms offered in Y-files. And as you can already see, the basic idea is that these nodes are placed very compact or are packed into a disk, very compact in a compact manner. And this can be used to just annotate, for example, group nodes with further nodes just by packing them into these nodes. And each node could then, of these grid nodes, could then represent some other information. Why do I mention this compact disk layout here at this point? Later on in the example, I would like to use it as a sub layout to express further information in our group nodes. And with this, I already would like to wrap up this with the layouts, this discussion with the layouts. If you are interested in more about this layouts, how to configure them, and what kind of possibilities do they have? So what kind of constraints can I express with them? So more from the algorithmic side and from a technical side, then I can recommend you the series on graph layouts and Y-files, which you can also find on our homepage on the subpage webinars, but also on YouTube. And there I explain many of these layout algorithms in greater detail. Or what you could also do is you could just go to Y@Live. This is also always a nice possibility to just play around with these layouts. So what you can do is you can just start with a sample graph. Let's take this one. And then you can just play around with these layouts here. So if you go to layout here on the left-hand side, And then what you can do is you can go to the organic layout, for example, or to the hierarchical layout maybe, and you can apply this layout directly on these nodes, and then you can see how it reacts. And then you can play around a bit with these layouts. Let's also take another one. Let's take yeah, the tree layout. And you can play around with this and see how they behave and what kind of basic properties they have. This is also a good starting point just by so what I also sometimes do is when I need to visualize data that I just take a subset of this data and I put it into y-add. So I just do this by clicking them together, and then I try to find out which of the layouts could be also suitable. So let's go back to the presentation. And what I now would like to do is to shortly sketch how we could create the layout for our example. And as I already said, I won't go very much into detail. There will be a follow-up webinar about coding where I really will discuss all coding details. But I now want to just give the basic ideas. So, and again, you will find this example in our playground. It's called Histories of Artists. So if you go to examples, code samples, you will find it here or also in the chat. There should be a link. And here, what you can see at the beginning, all these regions are collapsed so that you can only see the main part. And what I do is that I load the base graph and then I create another graph based on this. So basically, it's a kind of pre-processing, and then I apply the layout algorithms. So I just want to run the layout. So this was just computed on my computer within a second or less. And now we can have a look at this visualization. And as you can see here, what we have is these artists as thread nodes. And then we also have these group nodes here. And here you can already see why I've also talked about the compact disc. These group nodes representing music groups, so for example, the Beatles, also have nodes representing the genres of the releases and with respect of the number of releases per genre. So as you can see, the Beatles have really a lot of releases in pop and rock, but only few in blues. So this is what we can express. And what you can also see is that we have a temporal structure. So we have these bands that were founded in the 60s, 70s, and so on, and we have sorted them from top to bottom. And as I already said, I have applied the hierarchical layout on this graph structure. And the idea is then that we introduced some kind of constraints enforcing them to lie there. So for example, we said, okay, all these nodes here should lie above the nodes of the 70s and so on. And this is what you can easily express with our algorithms. Another thing that I would like to show you are the edge labels. So we also placed here edge labels representing the artist. So here, for example, Paul McCartney. So if you go along this line here, it's very easy to follow this path of Paul McCartney. And here at this point, you see here Paul McCartney, and you can go through this graph. In the later episodes, I will also show you other techniques like highlighting and animations that will help you to follow this path. So today it will be only about the layout, so where to place the nodes. So much about this visualization. Now I would like to show that we can create this step by step. So what you can see here is basically that we have loaded this graph. This is the graph that I've also loaded in the other example. And then I've called it time graph. I'm not sure whether this is the best name, but basically this time graph is then the graph that we actually would like to visualize. So here we actually have these paths going from starting at an artist, going through these music groups nodes. And then I create these layout configurations, which basically every time consists of a layout algorithm and then some kind of configuration. And what I can do, I can play around a little bit with this. What I can do is I just comment them out. And now I really only have the basic configuration for this. So I just say, without any constraints, without any further information, just create a layout using the hierarchical layout on the data set. And then I already get here this graph. So if I go to this, I don't explain this in detail. As I said, there will be a follow-up webinar. But as you can see, it's not very much code. It's basically just creating a hierarchical layout algorithm and then returning it after setting some basic properties. Oh. So, but as you can already see, the problem is with this that you already get some kind of temporal information here. So many nodes are already placed well, but for example, here we have nodes of the 70s, and here we have nodes of the 60s and so on. So this is not very well done with a basic configuration, and this is because the algorithm cannot know this, how to do this. So we actually need to introduce information. Another thing is that, for example, we have here this group Wings, and then also here this group Paul and Linda McCartney, and they both are from the same year. And actually, the data does not tell us which of these music groups was founded first. And of course, what we could do, we could annotate the data and say, okay, which was the first one, and then create the graph structure. But I didn't do this. So what I need to do is to actually to maybe introduce some constraints saying that these should at least lie on the same layer, so that there is not the visual impression that this group was founded first before this group, because this could be a wrong visualization. So what I do first is I introduce some same layer constraints, introducing constraints that say that groups that are connected and have the same year, so basically the same year of the first release, should be placed on the same layer, so should get the same y coordinates. So, and basically this, what this does is it also just configures the hierarchical layout, telling it in a very simple way how this should look like. And if we go, let's say, to the who and the high numbers, we can see here again, they have the same release date. So the first releases were in 1964, and now they are placed horizontally in the same layer. And the same should also be true for, here we have this Wings and Paul McCartney. So we have introduced very simple constraints, just expressing this visual information that the algorithm cannot know by itself. And what we can also do is, of course, what we would like to have is that we have some kind of structure, some kind of table showing that which nodes were in the 60s, which music groups were founded in the 70s, and so on. And to that end, we don't need to introduce for each of these groups single constraints, but what we can do is we can use or introduce a so-called partition grid, which is basically a table. And what we can then do is that we can just tell the algorithm which nodes should be contained in which cell of the table, or in our case here, in which row of the table. So basically this method basically just describes this partition grid. It introduces some distances, but it also introduces some constraints. It's basically here this line here only telling the algorithm that, for example, these music groups should be contained in the 60s, in the row 60s. Yeah, and then finally, the last thing that I would like to show is that we could also fill these nodes with further information, applying other algorithms. So for example, here what we can do is we can say, okay, we introduce new nodes for the shorers, and then we apply an algorithm on this subgraph here, and then we use this layout for this group node. And these are typical possibilities how you can use our layout algorithms to create such visualizations. If you are interested in more details about this, then as I already said, there will be a follow-up webinar on this. And I only wanted to give you some rough ideas about this. And this already brings me to the conclusion. And as you have seen, the analysis is an important tool for us for graph visualizations to gain new information in order to decide which kind of layout styles we would like to use, but we can also use it to pre-process the data. So we can annotate the data, for example, finding already important shortest paths, and we could say, okay, we annotate our data with this information in order to use this then later on in the visualization process. And in the layout part, you also learned that we can actually combine different layout algorithms with each other, and we can configure them using, for example, layer constraints, saying that nodes should lie on the same layer. So there are many, many different possibilities. And I only could give you a very small picture of this, but there's much more information about this. Altogether, so in the next, so this is one episode of several episodes. In the next episode then, so in February, I will talk about styling. So how to decide which colors to use, which shapes to use, which font sizes, but also more complicated things to decide. I will also introduce you to some of the most important design principles and so on. And then in the webinar in March, I will talk about interactions. So what kind of interactions could you introduce to your graph visualizations? For example, you could introduce animations, as I've done this here in this presentation, or you can introduce just very simple click interactions like highlighting and so on. So a small overview about the webinar. So this was the webinar today. And then there will be a webinar about styling in February, and then about interaction. And all of them should only give you some the overall ideas of this. And then there will be follow-up webinars for each of these, showing you actually how to do this in Wi-Fi's HTML. So these webinars will, so these for devs, will be really structured like this, that I really dive into the code and then I show you the details of this. And with this, I would like to wrap up the main part of this webinar, and I would like to start the question session. So the idea is now that I go through the chat and have a look at the questions, and then I will try to answer them. The first question is that the analysis techniques seem to be very general, and the question is whether they can be applied elsewhere. So of course, yes, there's a really large application besides graph visualization, where it's really about data analysis, but also in graph analysis, in graph visualization, I mean, you can apply graph analysis not only at the beginning, where it's about analyzing your data, find out how the data looks like, but you can also use it later on in the visualization process. So for example, if it comes to interaction and you would like to visualize the shortest path between nodes, then you could first, of course, you need first to compute this shortest path. You can apply analysis algorithms to then react on interactions. So this maybe is also a thing that I should mention. I showed you a very clear pipeline. Also in this very first episode, I showed you that you first need to consider the problem setting, then the layout, then styling, and then interaction. But of course, this gives you just a rough idea how to do this. But there are many interconnections, and sometimes it's good to go back and to do revise certain decisions. But it should give you a rough idea how to do this. And the analysis, for example, is one thing that you can apply in many of these parts. The next question. For which kind of developers are the developer webinars, which I just announced, which will be in April to June, because the participant wrote that the background is Java. So yeah, so the coding examples will be done in TypeScript and in Y-Files HTML. So basically in web development. But what I will do is I will focus on the really core parts of the visualization problems, which basically means that if you come from the Java side, for example, it will be no problem to understand what I will do in the code, and you can easily transfer this from HTML to Java, because also the API that we offer is very similar, or basically the same on the platforms with some few exceptions. The next question is how much what you showed today can be done with Wired, with a Wired graph editor, which I showed. So this online tool where you can click together these graphs. So basically, the Wired graph editor basically uses our algorithms that, or basically uses the Y-Files HTML library as a basis. And what you can do is you can create, of course, you can just use it as an editor, clicking graphs together, but you can also use it to apply the layouts. The question is, can I also do this the same things as I've shown in the webinar? Not all of them probably automatically. Of course, you can arrange these things by yourself. So, for example, introducing layer constraints for the hierarchical layout is not that easy, or it's not possible in Wired currently. But as far as I know, but the basic things you can do. So what you could do is you can create, for example, a basic layout with the hierarchical layout, and then you can also decide only to lay out sub parts of this and so on. But yeah, mostly this, if you really want to create complex graph visualizations with a lot of constraints, it often makes sense also to go the programmatically way. The next question, I have understood that each layout has a default edge router. Can we use another edge router for a layout? How can a custom edge routing affect performance? Let's say when we have 1,000 or nodes and 2,000 edges. Yeah, that's true that, or with other words, some of our layout algorithms have integrated edge routing. They do this on their own, and they just route the edges, or they have some additional information that they can use for the routing process. So, for example, the hierarchical layout has knows, of course, how the nodes will be placed, and this information will be used in order to do the routing. So it's kind of an optimized routing, which is done. What you can also do is you can use a generic edge router algorithm. So for example, in Wired Live, you can also find this edge router algorithm, which is then applied as an back as a post-processing step. So basically, all edges which may already be routed are just resetted to their original or to straight lines, and then it reroutes these edges as a post-processing step, which of course also means that it does not have all information. So often it is better to use the integrated edge routing and then to apply. But sometimes it's better, sometimes it's also good to use the edge routing stage. It depends much on your use case. About the running time, yeah, it depends very much on the layout itself. So especially for the integrated. So here it's really difficult to say certain numbers. And it depends very much also on how much space there is. So for example, if you have apply the edge routing algorithm as a post-processing step and all nodes are squeezed together and there's no much space, then it would take longer than if there's a lot of space. Such things will be important. I think this was the last question. And with this, I would like to wrap up this question session. I thank you for your attention, and I wish you a happy diagramming.